Um, Hello, can you hear me? Okay. Yes. Hello, everyone. My name is Yanwei Fu from Fudan University. Welcome to our CVPR 2022 tutorial about learning sparsity in neural network and robust static analysis. I'm the hoster. So this tutorial is collaborated with with Mr. Yikai Wang, Professor Yuan Yao, Dr. Xinwei Sun, and Professor Wu Taoyin. I share the screen, and you can see this is the basic schedule of our talk. And we spend 10 minutes to give the brief overview of talk, which is right now. First, I will give a talk about, give an introduction overview of our tutorial. Then Yikai, who is my PhD, will spend 20 minutes talk about sparse learning in noisy data detection. And Professor Yuan Yao will talk about inverse scale space method for sparse learning and statistical properties. And then we have 50 minutes break. After that, Dr. Xinwei Sun will give a talk about spatial learning in medical imaging. And finally, Professor Wu Taoyin will talk about learning to optimize algorithm unrolling. Basically, this tutorial will talk about learning sparsity, and we will give some algorithm statistical perspective, and also some application in computer vision and medical images. So, well, very welcome to this tutorial. I'll give some further details why we're using this title, learning sparsity in neural network and robust statistical analysis. Basically, we want to divide it into two parts. One part is learning sparsity in labels and data. One part is learning sparsity in deeper model. So we also have a website which is this URL. Maybe you can check the detail of our tutorial. We will put all the slides and talk online, and also some other material to support our tutorial. Let me share this screen about. So this is this is the web page of our tutorial website. Okay. So this is the overview of our tutorial, and let me start the first talk. So I briefly introduce myself since I'm the hoster. My name is Yanwei Fu from Fudan School of Data Science, Fudan University. Currently, I'm a tenure track professor. So I got my PhD from Queen Mary University of London in 2014 and worked as postdoc at Disney Research Pittsburgh from 2015 to 2016, and also got some awarded as a professor of Eastern Scholar and 1,000 young talents in China. I published more than 100 journal conference paper, including 10 PAMI paper. My research is about one-shot learning for image and videos and learning-based 3D construction for modeling object bodies and robotic grasping and image synthesis. Okay, thanks. Let me start my. Okay. So can I assume I'm sharing the screen, right? can you show? Can you?
Yes, we can.
Yeah. Okay. Great. Thank you. Okay. So let me start. Maybe I can wait another 2 minutes. Let's start from 9:14. Yeah. Basically, Xinwei Sun from Xinwei from also is my colleague from Fudan University, and Yuan Yao from Professor Yuan Yao from Hong Kong University of Science and Technology, and Professor Wu Taoying was a UCLA professor and now in Damo Academic Alibaba. So if any if you have any problem, welcome to email us, and we have the email address in the tutorial web page. Okay, let me wait for one more minute. Okay, probably I can start. So, welcome again. Hi, everybody. Glad to be here. My name is Yan Fu from Fudan University. So, let's start my tutorial. And this is the first part of our tutorial. I'll start from the motivation. So, let's give some overview. Probably some senior researcher know that 10 years ago, there's a very good tutorial, ECCV tutorial about sparse and low rank modeling given by Professor Yima, Professor Alan Young, and Professor John Wright. So it's about it's also about sparsity, low rank, basically sparse representation. Compared with that tutorial, our CVPR tutorial is more focused on learning sparsity in labels and data, which is good for robust statistical analysis, and also learning sparsity in deep model, which could produce compressive neural network. Oh, sorry. Maybe I can open the live script. Yeah, it's enabled. Open the live script. Yeah. So, our tutorial compared with that tutorial, our tutorial is more focused on deep learning sparsity in label and data, which is good for robust statistical analysis, and also learning sparsity in deep model, which could produce compressive neural network. So on the right figure, we give the schedule of our talk, and my senior PhD Yikai will give some more detail about my talk. Okay. So let's briefly review the ECCV tutorial about sparse and low rank modeling. Particularly, the sparse recovery data focus on the unmanned linear system, while the observation is much less than the unknown parameter, and the target is to extract compact knowledge from massive data. For example, in image compression, the input image can be decomposed by a small elements of DCT basis of be learned of as a learned dictionary. In recognition, the image can be represented with a combination of a training dictionary. And though this idea This simple sparse recovery of vector can be generalized to many other types of low-dimensional structure. For example, when we want to recover many correlated vector, that is a low-rank matrix, and we can formulate as a robust PCA problem. We can recover the phase and the varying illumination of recover the background images from foreground motions. So to solve this robust recovery problem, we aim to minimize the number of non-zero parameters of sparse vector under the linear constraint. However, this problem is known to be NP-hard and are hard to solve in general. Instead, when we find some convex alternative to this problem, a popular way would be replace the L0 norm with L1 norm. And when we further replace the square loss of the constraint to the Huber loss, which is very famous in statistics. So, like in the overview of our two paths, first is about sparse learning in date and label. Here, rather than recovering the sparse feature from data, we will consider the linear system with noisy data and label. Particularly, the label and the observation are noisy. So now we have a linear system with noisy label and data. And we will introduce works of recovering sparse noisy data label for robust statistics analysis. Here we have the equation Y is the noisy one-hot label, X is deep learning feature with coefficient. So we want to identify which Y is noisy. This is our the red font recovering sparse noisy data label, which we are focused on this part. It's different from the sparse learning sparse representation or sparse feature from data in previous tutorial. And we give the key formulation here. We introduce a sparse indicator gamma here. You can see the gamma. We call it a shifted linear system. Here, you can see that the gamma is a predict residue of the corresponding data. So if we can consider this case, we assume Y is noisy, one hot label, X is a deep learning feature with coefficient. So for clean data, gamma does not need to correct the prediction. That means we don't need the residue, the predicted residue, and this will lead gamma will be zero. We call it a zero shifted prediction. But for noisy data, the observed label is inconsistent with the Oracle linear model, and the gamma should be biased towards the prediction of the linear system to the cropped noise label. So here we for the noisy one hot label here the gamma should have some value. It should be zero. And this makes different. For clean data, we want the gamma to be zero, and for noisy data, the gamma should not be zero. And this is the shifted linear system. So by using this system, we can do the sparse learning for noisy data and labels. If you have any question, please list it in the chat box. And we compare and list some application that using this formulation. For example, in robust regression of classification, we can using this formulation. Basically here, beta we want to compute the beta. We give some example. This is a toy example, and the blue point indicate inner data, and the red point indicate the outlier data. And basically, this is the regression path we solve this linear system. We solve the objective derived from the linear system. And in statistical robust ranking, this formulation is used to solve the gamma and beta iteratively to progressively find the outlier and learn a ranking algorithm from noisy data. For example, this is a toy example, and the green line indicates the green edge indicates the inline voting, and the red edge means the outlier voting. And in face recognition, this formulation is transferred into a new standard linear system to recover the face under varying lighting of corruption of occlusion. And we'll give some details about this application in the next part of our talk, my talk. So before going into the detail, I would like to give some understanding about gamma in statistics. So basically, the gamma is the residue predicted error, which is a naive method to identify noisy data from the dataset. We can write the gamma as this equation, right? However, in general, this raw residue fail to detect outlier at leveraging point, as shown in the left figure. And a better way is using the leave one out externally studentized residue to test whether the predicted residue is a large value based on the other observation, right? This is basically equivalent to test whether the gamma is zero in this equation. However, this can only be used for only single outlier. When there are multiple outliers, there are phenomena we called masking and swapping. So masking means that multiple outliers will mask each other or help each other, and making all the outliers being undetected. Swapping means that multiple outliers may lead to large T residue value for clean data. In other words, swapping means that the algorithm will make the clean data as the outlier. So here, we'll consider the whole indicator matrix for all training data in the matrix formulation. Okay, I'll further give the overview of sparse learning in deep models. We want to learn effective sparse network structure from with good performance. This is the left side figure. For example, if compared with the densely trained model, the specified model will put a lot of filters and parameters at zero without sacrifice the generalization ability. This is why we want to learn sparsity in neural network. For example, in this example, the specified model, this particular layer is a particular convolution layer, and for this filter, we can simply drop this filter and only using this filter, and performance keeps the same. From a general perspective, we want to balance the model property of over-parameterization and compressive sparsity. So, despite the benefits of over-parameterization, a huge amount of parameter makes deep network too heavy in daily life application. On the other hand, training neural network without over-parameterization faces many practical problems. For example, being trapped in local optimum. So to sum up, in general, the success of DNN, deep neural network, relies on a huge number of parameters, while it hinders the deployment of unlimited resources machine. And the compressive network is desirable with less memory and completion cost. So this task is potentially very related to recent well-known foundation model, right? We highlight the dilemma of foundation model. A foundation model can centralize the information from all the data from various modalities like text, image, space, struct data, or 3D signal. And this foundation model can be applied to a wide range of downstreaming tasks. So to train the foundation model, I summarize a 4B, which means we need big data, right? We need a big machine, and we train big model. And that means we should have big money, right? Big fund. Realistically, it's only possible for very big company of agency. On the other hand, we want to use the foundation model for various tasks like question answering, sentiment analysis, image captioning, object recognition. But in adapting foundation model to specify downstream task, we need a prone the model. We need a prone irrelevant parameter and reduce model size. This can benefit deploying the model to specify the target task with limited resource machines. So essentially, we want to compress or specify the foundation model on this task, like robotics, like edge devices, self-driving cars. And there are a lot of great work recently on foundation model in computer vision and machine learning communities. It is actually quite topical recently. We summarize some recent foundation model, including CLIP, Alan, Abe, Florence, Nova, Intern, Gopher, Glevel, and Opt. So to some degree, it urges us to study learning sparsity in deep foundation models. Okay, let's give some detail on the first part, learning sparsity in data and label. We will give some application. The first one, we start from future learning task. So I assume we are very familiar. I assume the audience are very familiar with future learning. Basically, in future learning, we only have access to few label data to train the model. Furthermore, in industry, it is also cheap to collect massive, noisy, unlabeled data. So we can think the classic self-taught learning pipeline. So in the self-taught learning, we first train the future model with labeled image label pairs, and then we infer the pseudo labels for unlabeled data. We can further boost the future model with this pseudo labels image. Here, the core problem is that how to ensure the training with the pseudo label image is trustworthy, that the retraining will not damage the performance of original future learning model. That is very hard to do, as the pseudo labels are very noisy, and the future learning model is not trustable. So we'll show how to identify the credible ones from noisy pseudo label set. We will model the features and one-hot pseudo labels by our shifted linear system with noisy indicator. We solve this system and simplify to a standard linear regression of noisy indicator. Here, we're using the F norm, which corresponding to the penalty to the epsilon, and R is the term for the gamma. And to solve this linear regression model, it is important to select the prop lambda here, right? So let me think. The classic methods for selecting lambda would be heuristic rules, cross-validation, data adaptive technique of AIC-BIC. However, popular approaches are not applicable in our case. Obviously, each element of gamma is directly connecting to one image pseudo-label path. For example, in k-fold cross-validation, we will have some withheld data, and this data shall also have some corresponding gamma, which are unfortunately unable to be optimized in this case. That's why cross-validation cannot work here. And we will generate a solution path or regulation path to better identify the noisy data, and Yikai will give some details in next talk. We further give the application of training deep network with noisy label. So we propose to interactively do the feature learning and sample selection in the training time. The key difference from standard or vanilla deep learning training is that the training data is very noisy. So in the first stage, the network is trained with cross-entropy to extract features and classify label. As they are noisy labels, the network is not well trained. To solve this problem, we need to identify noisy data and remove them from the training set. So here, we assume a linear relationship between the feature and the one-hot labels. Interestingly, this linear assumption in general hold in many datasets, and we think it's reasonable because the deep learning, fundamentally deep learning is a representation learning, which means give some images of sentence, and we're learning some good features, and this feature should be the very nonlinear extraction from the image of data, right? And the backbone should be highly non-convex. And for the classification layer, and we can generally safe. It's safe to assume it's a linear relationship between the feature extracted and the final labels. And if we can check some recent works and a lot of works from Facebook and Google, they basically directly using the linear classifier in the final layer. And so those break this assumption, this linear abstraction will be identified as a noisy data. We solve this linear model with the sparse affinity on the noisy data indicator. And by using the solution path, we basically rank the data by the selecting time. And here, this is the solution path. Here, the axis is corresponding to the value of lambda, and the y-axis is corresponding to the magnitude of gamma. If we think that the lambda changing from infinite to minus infinite, and the value of gamma will be changed, follow the changing of lambda, right? This is the solution path, and This is and the here the blue lines indicates the clean data, and the red lines indicates the noisy data. And this is the end of the second stage, and means the sample selection. And we return to the feature learning stage and repeat these two stages entirely until converge. To further make the linear system scalable to large dataset, we first compute the class similarity matrix and divided the most dissimilar class into groups. So, and for each group, we select a small number of training data to construct small pieces of data, and then our algorithm will be running on each piece of data in parallel. Basically, this simplified our algorithm and make it scalable to large dataset. Our shift linear system can also be used for cross-sourcing ranking task. Particularly, given two paired images, we can do the cross-sourcing and ask a lot of people to give the voting. Interesting, this task is very related to the task of named learning relative attributes in computer vision. For example, the man, the B in figure B, is less smelling than figure A, but more smelling than figure C. And the figure E is less nature than figure D, but more nature than F. So basically, in relative attribute, we have some, for relative attributes means that we have some attribute. It's very hard to give 0, 1 labels, but we're using the relative comparison to help label the images of data. And in computer vision, we call this task as the subject visual property. So for the cross-sourcing data, even using the paired comparison, this data will be very noisy due to many factors. For example, character factor, and psychological factor, ambiguous comparison of lazy annotator. For example, I gave the figure here. Yao Ming has some special faces, and Asian people will think he's smiling, but in general, it's ambiguous. It's an ambiguous instance. Here, I'm using one toy example to show how we construct the learning sparsity for robust ranking. For the left figure, we do the age estimation. We collect some cross-sourcing path, which indicates by the direct edge. And the red edge means outlier voting, and the number here means how many people do the voting. So the model will learn on the left subfigure and will give the prediction of the age on the right two photos. For example, here, that this edge means that two persons think the person in this image is older than the person in this image. Obviously, this is outlier voting. And by using this cross-sourcing path, we construct direct graph. V and E. V means the node, and for each node, we can extract a feature. We indicate the phi. Phi I means the feature for image I, and phi G means the feature for image G. And we introduce the shifted linear system and using gamma IG to indicate whether the bolting YIG is outlier or not. And furthermore, we can write the dataset into the matrix formulation. Here, the C is the instance matrix, and the phi is the feature for all nodes, is the feature matrix for all nodes, and beta basically is a coefficient. And basically, we still formalize as these objectives, and we using SVD decomposition on this C phi matrix, and we can simplify the gamma as this objective. So, interestingly, this leads to a precondition lasso problem. This is a precondition lasso, and to solve this objective, we basically still checking the regression path. Here we give a toy demo to visualize the solver. The blue point indicates the inline, and the red point indicates outline, and we basically using this precondition lasso formulation and check the regression path. And here the axis is still the lambda, and y-axis is the magnitude of gamma. Basically, following the regression path, the outlier variable will come first, which is the red line here, and the blue lines indicates the inline. So now I also talk about the learning sparsity in neural network. In general, we like the idea of over-parameterization. We like the over-parallel network, which have good expressive power. However, we do not like a million parameter, which are hard to be used in many real-world applications like robotics or self-driving car, right? Therefore, the compressive network without losing of performance is desirable. So to achieve this goal, researchers basically proposed two-stage approaches. First, fully train dense network, then find good sparse subnet. And there are a lot of common practice of old school techniques like network pruning, regression, knowledge residual, and recently proposed lottery ticket hypothesis. Unfortunately, without over-parameterization, compressive model, if directly trained by optimizer, such as SGD, may be trapped in local optimum. In contrast, we're thinking a one-stage approach without fully trained a dense network. So let's briefly review previous work, regression and over-parameterization. Existing work leverage the regression, such as L1 regression, which enforces sparsity on neural network of L2, such as VCK. However, training with regression can decrease the capacity of network, leading the local optimum. A series of recent work have found the advantage of over-parameterization model in terms of optimization and generalization. So training over-parameter model can be viewed as a linear approximation to the network function, which makes it easy to find global optimum. In addition, the wayside dependence complexity as multiplied terms of Lipson's constraint are controlled, which can explain the better generation it obtained. However, the overpower model suffers from large inference time and memory cost. As for network pruning, pruning is actually one of the most straightforward and direct way of producing a light model. And network pruning can be roughly categorized as a weight of filter pruning by checking whether removing some structure parameters such as convolutional layers. And the common practice of pruning would be first we first by learning connectivity by non-network training, and then prune the low-weight connection and retrain the network to learn the final weights for the remaining sparse connection. And we listed some works. This example paper from Dr. Song Han from MIT. Actually, Dr. Song Han have a lot of work on this. Also, it's a quite related topic is quantization, which is useful for hardware acceleration. So our question here, can we do the sparsity in a unified algorithm? In the sense that we want to do the pruning in weight level, filter level, or even layer level. Can we do that? This is a question we can ask. Also, there are some other works of learning sparsity on transformer. This is like this work of pruning over parallel structure with recurring. So this is a recurring model structure, which is very interesting and partly inspired our algorithm. And the knowledge seal is also a well-known concept. In distillation, the knowledge is transferred from the teacher model to the student model by minimize a loss function, typically in which the target is a distribution of class property predicted by the teacher model. So this is a knowledge seal. There are actually quite a lot of work on this topic. Another interesting hypothesis has been proposed recently, named the lottery ticket hypothesis, which is defined as defining the winning tickets as the subnetworks which can obtain comparable result to dense ones if trained in isolation. This is a very famous idea, and I think this paper won the best paper award in iClear 2019. However, Pritz's work revents from initialization to find winning ticket subnet, which is very consuming. So we're thinking whether we can do it cheaper, right? For example, with early stopping, whether we can find some sparse subnet as winning tickets in lottery ticket hypothesis. This is actually inspired our work next. This is the key idea of our work. We propose optimizer named Dataset, which is the abbreviation of deeply structured splitting linearized Bregman iteration. Here, basically for our parallel network in space W, we basically lifting the parameter W to W gamma. And W is the training overpair model, and gamma introduced to learn structure sparsity in inverse scale space. we make a dynamic training algorithm named linearized Bregman iteration to train the dense overpair model by W and structure sparsity by gamma simultaneously. And the structure sparsity learned by gamma provide a good candidate for subnet structure. Here, we expect that the more interpretable feature should be selected, while others do not in the inverse scale space. This is actually the nice property of inverse scale space, with the scales implying the selection time of feature. And Professor Yuan will give more details about the inverse scale space from a statistical perspective. And the larger the Panty parameter induced more sparsity of the model. For example, in image classification, the shape-based feature select first and the cost-found feature select later. And then we using LBI and get the compressor network WS. Here, basically, this is the operation of lifting to the by introducing inverse scale space and using LBI to solve it, which combine together, we call it DES LBI. This is our advisor for this talk, and we'll give some mathematical and statistical introduction of LBI in the next talk. So why we come up with this idea? Basically, compare with the two-stage method, our key insight is to lift the model parameter space by using inverse scale space. This is actually motivated by the PointNet. Here, PointNet is a method to analyze the point data, and it's aggregate in high dimension space, preserve interesting property of the geometry. So it's also using the idea of lifting the 3D point to high space and then do the max polling, right? And we give some more intuitive insight of our method. Here, this is the illustration. In the original over-parameter space, the WS denotes the sparse parameter, which can be the winning tickets, and WSC is a complementary of the space WS. So due to the highly correlated WS and WC, it's hard to identify the good WS, basically. But if we think we lifting W and gamma into a high dimension space, the WS and WC can be quite likely be orthogonal, making WS easily to be identified. And we update the loss by using additional L2 regulation here to keep the gamma and W close enough. All right, and our formulation is the differential inclusion of inverse scale space, and we introduce Vt as the dual parameter of gamma t, and the Wt basically follow the gradient descendant with L2 regulation. And equipped with this, the important feature of gamma t are easily first selected. Also, it enjoys a simple discretization version. We call it DES LBI. Basically, it's this formulation, and we divided this formulation into two parts. The first part is still the Wt is a gradient for W and the proximal mapping for gamma. Okay, let's give more detail about proximal mapping. The proximal mapping basically controls the sparsity, right? The proximum operator basically project the dual element V into a prime element with sparsity enforcement. And the general form of gamma induce a Bregman distance. Here it degenerated to Euclidean distance with 1 omega is L2 distance. And the omega can be selected as group sparsity for filter and L1 sparsity for neuron in fully connected layer. And we list here. Interesting is enjoy a closed form solution. And also, our algorithm can be easily adapted to various forms, such as training with batch samples and with momentum and with decay. We present a theory in our paper shows that our optimizer is guaranteed the global convergence from any initialization. The Dataset API converts to a critical point of our algorithm assume the most defendable activation. Relu could be approximated by soft class. If you want to check the detail, please refer our PAMI paper here, this paper. Okay, this is some discussion about proximal mapping. Actually, this is our PAMI paper is quite long about this theoretical and different version of our Dataset API optimizer. I've given a lot of experiments and in our paper. Here we select some. As an illustration, we show the Dataset API on main amnesty set. The left is our training path, and the right is a visualization of filters selected by gamma. And the x-axis is the training epochs, and the y-axis is the magnitude of filter. And we select 3 times 20, 40, 80 epoch. And we visualize the corresponding filter, and we show that our Dataset API make a very sparse filter, and in contrast to SED, a lot of filter are not sparse, right? And we also give example as we start our story starting from the winning ticket. So we can show that by using Dataset API, it's easy for us to identify the winning tickets. This is our result of the retraining subnet selected by gamma. So first we train the Dataset API with early stopping. Actually, we can only train like 2, 4, 8, 16. We try different epochs with early stopping. And then we find extract the gamma as a subnetwork structure, and then we retrain the subnetwork, and we find the winning tickets. Here we show that on today's set, this is our result. It's much better than the baseline node. Means that our Dataset API can successfully identify the winning tickets structure. Finally, we write a very easy to use the toolbox. This is the GitHub homepage of our project. Basically, it's install free. We just put the Python file into the project folder and import them. You can using the Dataset API optimizer just as SGD in Python, in PyTorch. I'm also give some example to train the network by using internet dataset, which is this script. And our network optimizer can find important structure sparsity, have short train time, can explore the regression path, and a lot of interesting property. And we can also give the script to do the network pruning. Basically, by using the information from augmented variable gamma, we can do the network pruning. And we also can do the green network. We add the new filter according to the support set of augmented gamma to enlarge the model capacity, which is a very interesting application. Basically, we can start from a very small network and using our optimizer to train the model, and then enlarge the model and train the model at the same time. So finally, we give some brief discussion about our algorithm from ADMM, which is also adopts the idea of variable splitting. So the biggest difference is that ADMM is an optimization algorithm, which is converts to a minimizer of a loss with a fixed regression parameter. In contrast, DESI is a discretization of a differential equation, which generates a sequence of model from simple to complex, corresponding to different regression parameter. So the idea here, we basically care more about the regularized solution path. Okay, it's time I'll end here. So thanks. If any question, please email me, and let me check whether there's any question. Let me stop sharing. Okay. Any question?
Maybe I have one small question. Just now you mentioned the maybe the finding the sparse transformer, or before that some work you said maybe inspired by your algorithm. What's the idea of that application or that work? How this connection becomes?
Oh, you mean?
I guess it's somewhere maybe before the sparse transformer or something. Yeah, this one.
This one.
Yeah.
Right.
I guess. Yeah.
So, thanks for this question. Interesting. Actually, very interesting. Basically, we know that transformer has a lot of parameter, and basically we want to do the pruning and make a transformer sparse and make the transformer useful to a lot of like robotics or for self-driving car. The key difference that we are doing the learning sparsity on deep model by using our algorithm, by using our optimizer from a optimization perspective, rather than directly do the sparse, rather than directly design sparse transformer. So in this work, basically they design the sparse transformer, and it's kind of two orthogonal task, or two orthogonal method. For this task, for this design sparse transformer architecture, they can also using our optimizer and optimize the model, and we can identify the redundant parameter and remove them. Yeah, it's actually the future work to give a more solid experiment to test whether optimizer can well be used to transformer. Right. That's my think.
Okay. Yeah. Thank you. That's very expensive for transformer training.
Yeah. But with the development of GPUs, I think it will be solvable. It's much cheaper. For example, like 2 years ago, 4 years ago, the GPU the GPU memory is compared with nowadays GPU memory is totally totally different. 4 years ago, we cannot afford to even train a transformer. Now we can do much better. Yeah.
Okay.